Hello everyone and welcome to my channel Chemistry by Miss Nithi Banga. Today we will be talking about reasoning or conceptual questions from Haloalkane and Haloarenes. So let's get started. Our first question is, explain the reactivity order of Rx, Rf, RCl, RBr and Ri towards nucleophilic substitution. So the order is actually this. Why? Because whether it's SN1 or SN2, this is going to be the order. Now our R group is same in all of them, only the halide is different. So here in Ri, our iodine is the largest atom. Out of all the halogen atoms, iodine is largest. Therefore, the bond length between carbon and iodine is the longest. And whether SN1 takes place or SN2 takes place, halide ion has to leave. So if the bond length is longer, carbon-halogen bond length is longer, it's going to be easier to break it, right? So that is why Ri will have the highest reactivity towards nucleophilic substitution, whether it's SN1 or SN2, owing to its long bond length, therefore weaker bond, therefore easy to break. Okay, moving on to explain the density order of CH3, CH2Cl2 or CHCl3. So what's different in all of them? The difference is number of chlorine atoms. And what is density? Density is mass by volume. So mass here would be different for all of them because chlorine is much heavier than hydrogen, right? So a compound with more chlorine atom is going to have much more mass than the one which has lesser number of chlorine atoms. Now, what about volume? Volume is going to be more or less the same because they all have tetrahedral shape and only one atoms. So volume is more or less the same. It's the mass that changes drastically. And mass is much more for this, and then this. So the order of density would be CHCl3 highest, followed by CH2Cl2, and then last would be CH3Cl. Okay, moving on to the next question. Haloalkanes are only slightly soluble in water despite being polar. Justify. Okay, so these are haloalkanes and the interaction between them would be dipole-dipole interaction. Dipole-dipole interaction because there's a dipole between the carbon and the halogen atom. Water, the intermolecular interaction between water molecule would be a strong hydrogen bond. Okay, so this interaction is much stronger. Now, if we mix them, the new interaction that would be formed would be dipole-dipole because the hydrogen bonding is formed only between hydrogen and nitrogen or oxygen or fluorine. Okay, so this interaction is going to be dipole-dipole. Now, this interaction is much weaker than the hydrogen bonding that is present between water molecules. Okay, so the new interaction between Rx and water are not as strong as the hydrogen bonding in water. That is why haloalkanes are only slightly soluble in water despite being polar. Next question. Explain the melting point and boiling point order of dichlorobenzenes. So these are the dichlorobenzene, orthoisomer, metaisomer and paraisomer. The boiling point trend is this, ortho being the highest, then meta and then para. These are actually more or less the same. So now why orthoisomer has higher boiling point than the other two? It's simply because this carbon-halogen bond is polar, right? This carbon-halogen bond is also polar. And since they are joined, they are very close to each other, so the resultant dipole moment is going to be bigger, right? So this molecule is polar. Whereas here, there's a dipole here and then there's a dipole here. They are a little bit away from each other. So the resultant dipole would not be as great as in this. Here, the dipoles are actually in the opposite direction. So they cancel out each other completely. So this one is non-polar. Okay. Now, when we are talking about boiling point, the factor that influences boiling point the most is intermolecular forces. Intermolecular forces in this case would be dipole moment. Dipole-dipole interactions. And here would be van der Waals forces because there is no dipole here. And dipole-dipole interactions are stronger than van der Waals forces, right? Therefore, the boiling point of one would be much greater than that of second or third. Now, talking about melting point. When we're talking about melting point, we are talking about solids being melted. Now, when we talk about solids, in solids, the particles are very closely fit together, right? The closer they are, more energy would be required to pull them apart. And out of these, the one that fits very nicely in a structure, in a closed packing is this one. Okay, because of its symmetrical structure. Because of its symmetrical structure, it would be very nicely packed. Whereas this one and this one, they're both not as symmetrical and therefore the packing would not be as close, right? So because of the close type packing, in this case, because of its symmetrical structure, it will have much higher melting point than the other two. Okay, moving on to the next question. Boiling point of bromoethane is higher than that of chloroethane. Yes, of course it is higher because boiling point is directly proportional to molecular mass. It's also influenced by intermolecular forces and branching. But here the factor that is working is molecular mass because bromoethane has more mass than chloroethane because bromine has higher atomic mass than chlorine. Okay, that is why bromoethane has higher boiling point than chloroethane. Okay, next one. Preparation of haloalkanes using SOCl2 is considered the best method. Why? So, when alcohols are combined with SOCl2, the products that are formed are RCl, SO2 and HCl, and these two are gases, so they can escape. When they escape, all that you are left with in the reaction mixture is your pure compound, pure product. Okay, all right. Okay, next question. Preparation of iodoalkanes using sodium iodide and sulfuric acid is not possible. Explain. So when we prepare alkyl halides using alcohols, we actually tend to use sodium bromide with sulfuric acid because they will combine together and will produce HBr in situ. Now this HBr will combine with the alcohol and will give RBr and rest of the products, right? We cannot use the same technique for preparation of alkyl iodide. Why? Because when sodium iodide and sulfuric acid combine, they would produce hydrogen iodide. That is true. But sulfuric acid is also a mild oxidizing agent. So as soon as HI would be produced, it would be oxidized to I2. And now your reactant, which was to react with ROH to produce Ri, is consumed, is oxidized to I2. So it's no longer available, right? So this reaction does not proceed. Now, you might ask that why doesn't that happen with HBr? It doesn't happen with HBr because, like I said, sulfuric acid is a mild oxidizing agent. It's easier to oxidize HI to I2 than HBr to Br2. This is not carried out by sulfuric acid. Sulfuric acid is just not strong enough to oxidize HBr to Br2. Okay, moving on. Why should Grignard reagent be stored under anhydrous conditions? So these are your Grignard reagent. When it combines with water, water has H plus and OH minus ions. Now since this is partially negative, H plus would combine with this and will form the alkane and will be left with MgOHX also. Now, if Grignard reagent is to be stored for further use, we cannot afford to have moisture in it because moisture or water will then be reacting with the Grignard reagent and it will form alkane. We use this very reaction to form alkane from Grignard reagent, but for storing purpose, we cannot afford to convert all of it into alkane, right? For this reason, the solvent that we use while carrying out Grignard reagent reactions is dry ether. Dry ether doesn't mean that it's not liquid. It is very much liquid, but dry means that it does not have moisture. It doesn't have moisture. That means no water molecules. Because if we don't have dry ether, if there is water in the solvent, then again, let's say you wanted to combine RMGX with RCN. But now since the solvent contains moisture, some of the RMGX would combine with moisture and will form alkane. And you will end up with many products, the product that you were expecting, wanted to make, and then this unwanted alkane, which you did not want to make, right? So it's important to use dry ether while carrying out reactions with Grignard reagent. Moving on to the next question. Explain the use of dry acetone as a solvent for Finkelstein reaction. Now this is your Finkelstein reaction. Now we use dry acetone in this because dry acetone, because this NaI is soluble in dry acetone, whereas the byproduct NaX, which may be sodium chloride or sodium bromide, they are both insoluble in dry acetone. So what happens is we would obviously want our reactants to be soluble in the solvent that we are using, but then if one of the product, the unwanted product, is insoluble, then it settles and we can remove it by filtration. In that case, in reaction mixture, we will have our pure product as the desired product. Also, because when we remove this product, the reaction also moves forward in order to make more of the product, right? So this is the use of dry acetone. Moving on to the next question. Halobenzene is slightly deactivating despite showing plus R effect. So yes, halobenzene shows plus R effect, okay, and increases the electron density on the benzene ring, but it also shows minus I effect, okay, minus I effect because of the halogen atom. So because of this minus I effect, it sort of pulls the electron density from the benzene ring. Now these two effects have opposite impact. Plus R effect increases the electron density, minus I effect decreases the electron density. Now minus I effect outweighs the plus R effect. Okay, minus I effect outweighs the plus R effect. That is why halobenzenes are slightly deactivating. Next question. Allylic and benzylic halides prefer SN1. So this is your allylic halide and this is your benzylic halide. They prefer SN1 because in SN1, the first step, the halogen atom leaves. When the halogen atom leaves, you are left with carbocation. So it proceeds via the formation of carbocation. Now this carbocation, which is the intermediate in SN1 reaction, is very, very stable. How? Because of resonance in the allylic group. Okay, because of this resonance, this carbocation is stable. Therefore, the reaction proceeds further. Same is the case with benzylic halides. Here also, after the halide atom leaves, halide ion leaves, benzylic carbocation is formed, and this benzylic carbocation is very stable because of the resonance. Right? Moving on. Vinylic and aryl halides do not undergo nucleophilic substitution. So now this is your vinyl halide and this is your aryl halide. Now, if you look at the structure, you will see that there is resonance here. And because of the resonance, there is partial double bond character. So this CX bond acquires a partial double bond character because of the resonance, right? Same happens with aryl halide. There are other reasons for it to not give a nucleophilic substitution also. Partial double bond character is one reason. Because of this partial double bond character, this bond is very strong, very difficult to break. But then that's not all. This is sp2 hybridized and so is this. Okay, when they are sp2 hybridized, that means this carbon is also electronegative and your halogen is also electronegative. When both are electronegative, the electrons more or less are in between the two. So that means there is no polarity of CX bond. If there is no polarity of CX bond, or at least we can say that the CX bond is not as polar as it would be if the carbon was sp3 hybridized. Okay, if this was sp3 hybridized, this bond was polar. Okay, so nucleophile can attack this carbon because it gains partial positive and the halogen atom is partially negative. But if you, in case of vinylic and arylic halides, what happens is the C, which is attached to the X, that is your halide, is sp2 hybridized. sp2 hybridized carbons are electronegative. So electronegative means that the electrons would now be more or less in the middle, this bond would not be as polar. If it's not polar, the nucleophile would not be able to attack. Another reason for arylic halides to not be very keen on nucleophilic substitution is that benzene ring is very electron rich. So since it's electron rich, the nucleophile would be reluctant to even approach, right? Because this is very electron rich and nucleophile also is electron rich. Okay, so there are many reasons. You can write first one as partial double bond character, making CX bond very strong. Then second thing is the sp2 hybridization of the carbon in the CX bond, which makes it less polar, or you can say that which decreases the electrophilicity of the carbon here. Therefore, vinylic and arylic halides are not as keen to nucleophilic substitution. Next question. Give uses of Freon 12, DDT, carbon tetrachloride, and iodoform. So, iodoform is an antiseptic, okay? You may remember this from the tincture of iodine as well. Tincture of iodine is also antiseptic, so that helps in remembering. Carbon tetrachloride is a solvent. It's also the main reactant when we want to produce chlorofluorocarbons. And then this is not anesthetic. CHCl3, that is your chloroform. That chloroform has anesthetic properties, right? But CCl4, carbon tetrachloride, is a solvent and it is used for production of chlorofluorocarbons. Then we have DDT. DDT is an insecticide. Now these two are not uses of DDT, but it's important that you know that DDT is chemically very stable. And if it enters into the food chain, its concentration in animals builds up. This is called as biomagnification. Okay. Next, Freon 12. Freon 12 is dichloro-difluoromethane. It's used in aerosol propellants. It is also, as actually all chlorofluorocarbons are used as coolants in refrigeration and in air conditions. Next up is, explain the different products formed when RX is reacted with KCN and AgCN. Okay. So when RX is reacted with KCN, KCN being an ionic compound breaks into the two ions, potassium ion and cyanide ion. And then cyanide ion combines with R and forms RCN. Cyanide actually can attack from nitrogen also, but since the carbon-carbon bond is more stronger than carbon-nitrogen bond, it prefers to attack from carbon end. Okay. But when Rx is reacted with AgCN, AgCN is covalent. Since it's covalent, it doesn't break into ions. And then only nitrogen's lone pair are able to attack the carbon in the alkyl halides, forming RNC. This you can remember this way also. Whenever there is silver compounds being covalent, only nitrogen would be able to attack. So in case of silver compounds, the attack would always be from nitrogen, and nitrogen would be joined with carbon of the alkyl group. Next up, why should chloroform be stored in dark colored bottles? And actually those dark colored bottles need to be completely filled with chloroform up to the brim. Now why is that the condition? Because when chloroform combines with air, if you don't fill it to the brim, there would be air here, and then that air in presence of sunlight combines with chloroform to form a toxic gas, that is phosgene, and HCl is produced. So this reaction is very simple. Just remove one H and one Cl and place an O instead of these two, and now balance the reaction. Here you go. Okay, moving on to the next question. Explain the boiling point order of N-pentyl chloride, sec-pentyl chloride, and neopentyl chloride. So these are the structures. This is N-pentyl chloride, this is sec-pentyl chloride, and this is neopentyl chloride. So you can see that N-pentyl chloride is straight chain. Here there is a little branching, and here there is a lot of branching. So how does boiling point depend on branching? Boiling point is inversely proportional to branching. Higher the amount of branching, lower is the surface area. If lower surface area, see, this has a longer surface area, this has a larger surface area. This is more or less a circular shape, a globular shape. So its surface area is much less. Okay, so what happens is, why is surface area important? Because van der Waals forces depend upon surface area. Higher the surface area, higher is the force, higher is the van der Waals interaction between two N-pentyl chloride molecules, and therefore more would be the boiling point. Next question. SN2 leads to inverted product formation. Explain. So if this is your alkyl halide to begin with, this is your nucleophile, this will attack from a side which is opposite to the leaving group. Okay, and then as the nucleophile would approach, these hydrogen atoms would move away from it so as to make more space for it. And ultimately, in the transition state, they will form this structure, trigonal biplanar. Okay, and once this bond is broken, then they would rearrange themselves to resume that tetrahedral shape again. So now since nucleophile is attacking from the opposite side, and because of this, there is inversion. You see, if you see the reactant configuration and this product, you would see that there is inversion of configuration. Okay, moving on to the next question. SN1 is promoted by polar solvents. Why? SN1 is promoted by polar solvent because it proceeds via formation of carbocation, and polar solvents can stabilize carbocation. How would they stabilize? Let's say this is the carbocation. Polar solvents, let's say water is a polar solvent. So the negative end of the polar solvent would make a solvation sphere around the carbocation. So that would stabilize the carbocation. Okay, moving on. Okay, so SN1 reaction of optically active haloalkanes leads to racemization. Explain. So this is your optically active haloalkane. Why it is optically active? Because this carbon is chiral. It is attached to 4 different groups. Now, when it proceeds to SN1 mechanism, when X leaves, a carbocation is formed, and in this carbocation, it resumes a trigonal planar geometry. Okay, in this carbocation, the nucleophile can attack from both sides. Okay, so if it attacks from this side, retention of configuration would be seen, and if it attacks from the other side, inversion of configuration would be achieved. So in these cases, these two are enantiomers. These two are enantiomers, meaning that one of them, we don't know which one, but one of them would rotate the plane polarized light towards the right, and the other one would rotate PPL towards the left. So resultant would be a racemic mixture. Okay, moving on to the next question. Draw the enantiomers of 2-chlorobutane. Now 2-chlorobutane is optically active. How would you draw the enantiomers? You first draw it in a tetrahedral geometry, and in that make sure that 3 of them are in one plane. One of them is coming out of the plane towards you, and the other one, the dashed bond, is away from the plane, on the other side of the plane, away from you. Okay, when you draw the other enantiomer of this, just draw the mirror image of it. Okay, these two are mirror image. So these are your enantiomers. Moving on, how do we or why do we use nitric acid or HiO3 for iodization of benzene? Now, if we have to do like chlorination of benzene, what do? We take benzene and then chlorine and then anhydrous AlCl3, right? Friedel-Crafts chlorination. Now what happens is chlorine gets attached, right? And HCl is formed. Now, when we talk about iodization of benzene, this is not possible. Why? First of all, benzene is not very keen on bonding with iodine because carbon-iodine bond, as we know, since iodine is a big atom, the carbon-iodine bond is longer and therefore weaker. So benzene is not very keen on making carbon-iodine bond. So, but if this reaction proceeds, it is reversible for this reason, right? Now, the byproduct is HI. So if we want the reaction to proceed, what we can do is we can add an oxidizing agent, HNO3 or HiO3. These oxidizing agent would convert HI into I2 and therefore they would remove it from the reaction mixture and then the reaction can move forward. Moving on, what happens when ethyl alcohol reacts with HI in presence of Ki and H3PO4? So what happens is normally it's the same reaction as when we discussed NaBr plus H2SO4, right? But we cannot use H2SO4 for iodine because it's an oxidizing agent. So what do we use? We use orthophosphoric acid. Now, in presence of orthophosphoric acid, which is not an oxidizing agent, it will not oxidize HI. The HI that forms here, okay, it will not oxidize that. Therefore, HI would be available for nucleophilic substitution. Therefore, your product would be formed, okay? Next question. Write the IUPAC name of major product formed when 2-bromobutane is treated with alcoholic KOH. When we talk about alcoholic KOH, the reaction that takes place is beta dehydrohalogenation. Dehydrohalogenation. So if this is bromine, this is the alpha carbon, this is the beta carbon, therefore this is the beta hydrogen. This is also beta hydrogen. Now how the reaction proceeds is a base, this KOH being a base, it will abstract the proton. These electrons would be shifted here and bromide would be released. Okay. In that case, the product formed would be this. Okay. But if base abstract this proton, in that case, these electrons would shift here and bromide would be released and this product would be formed. Right. Now, which of the two products would be major? Both will be formed, but major would be this. Second, because second one is more substituted. This is explained by Zetsef rule. Zetsef rule says that more substituted alkene is formed. Now, how is that more substituted? Look across the double bond. This is one substitution and this is another substitution. Whereas when we talk about this, across the double bond, on this carbon, there is no substitution. There is only hydrogen. Whereas on this carbon, there is one substitution. So in total, one substitution here, but two substitutions here. So this is more substituted and therefore will be the major product. Moving on. Why are tertiary alkyl halide practically inert to substitution by SN2 mechanism? In SN2 mechanism, we know that nucleophile attacks the carbon while the X is still attached to it, right? So if there are three bulky groups here already, the nucleophile would not be able to approach. Okay, so the short answer is steric hindrance. Because of steric hindrance, alkyl halides, tertiary alkyl halides are inert to substitution by SN2 mechanism. Moving on. Why does triiodomethane have antiseptic properties? Because triiodomethane liberates iodine and this iodine is the one with antiseptic properties. Okay, moving on. Which alkyl halide from the following pair is chiral and undergoes? Okay, among the isomers of pentane, these are the isomers of pentane, which one on photochemical chlorination yields single monohalide? So when we react alkanes, or in this case pentane, with chlorine in presence of UV light, photochemical chlorination takes place. And let's say we are making monohalide. So when monohalide is formed, it can form in this isomer, it can form here or here or here. Okay, chlorine atom can get substituted here or here or here. So it will give 3 monohalides. When we talk about this structure, the chlorine atom can get substituted here or here or here or here. So 4 monohalides are possible. But when we talk about neopentane, the chlorine atom cannot get substituted here because there is no hydrogen here, and all these carbons, they are practically the same. So if it gets substituted here or here or here or here, it would be the same, right? So this is the isomer of pentane, which on photochemical chlorination will give a single monohalide. Next question. Alkyl halides react with lithium aluminium hydride to give alkane. Name the attacking reagent which will bring out the change. So this is your RX, haloalkane. Lithium aluminium hydride has hydride ion. So it's the hydride ion with the negative charge which will attack on the carbon of the haloalkane and therefore will form alkane. Now, talking about attacking reagents, let's also discuss what would be the attacking reagent when chlorination takes place on benzene. Benzene is an electrolyte-rich compound, so obviously electrophile would attack on it. Now what would be the electrophile here? Electrophile cannot be chloride ion. It has to be chlorinium ion. Okay, so please remember this. Whenever there is a substitution, electrophilic substitution taking place on benzene, only an electrophile, that means something that is electron deficient, would attack the benzene ring. Okay, so the attacking reagent here is chloride. When we talk about nitration, HNO3 and H2SO4 mixture we take, right? In that case, the attacking reagent is not nitrite ion. No, it's nitronium ion. Okay, this is very important concept. Okay, now moving on. Plus minus 2-butanol is optically inactive. Give reasons. So this plus means that this is basically plus minus together means it's a racemic mixture. Okay, which has equal amount of plus isomer and minus isomer. That means equal amount of dextrorotatory isomer and levorotatory isomer. And it's optically active because the dextrorotatory will rotate the PPL clockwise and levorotatory will rotate it anti-clockwise. So basically they will cancel out each other. The rotations will cancel out each other and it would be optically inactive. Moving on, CCl bond length in chlorobenzene is shorter than CCl bond length in chloromethane. So in chlorobenzene, CCl, this bond is shorter. This is obviously shorter because resonance takes place and this CCl bond acquires a double bond character. And since double bond is shorter than single bond, even partial double bond would mean that this bond would be shorter than single bond, although longer than double bond. But still, it would be shorter than the single CCl bond, which we have in chloromethane. Next question. Dipole moment of chlorobenzene is lower than that of cyclohexyl chloride. So this is chlorobenzene, cyclohexyl chloride. Dipole moment of this bond is lower than dipole moment in this bond. The only difference between these two bonds is that this is sp2 hybridized carbon and this is sp3 hybridized carbon. sp2 hybridized carbon means that this is more electronegative since it has higher s character. Higher s character means the s orbital, which is closer to nucleus, can hold on to electron more tightly. So sp2 hybridized orbitals or sp2 hybridized carbon would be more electronegative. So if this is electronegative and halogen atom is also electronegative, so this bond is not going to be very polar. Okay, whereas here this carbon is sp3 hybridized. This is not electronegative, whereas chlorine is electronegative. So it will pull the electron towards itself and this bond would clearly have a higher dipole moment. Moving on to the next question. Presence of nitro group at ortho and para positions increases the reactivity of haloarenes towards nucleophilic substitution reaction. So if this is your chlorobenzene, if you have nitro groups at ortho or para position, it will decrease, since these are electron withdrawing group, it will pull the electron density from the benzene ring and therefore nucleophile will be able to attack. So electron withdrawing group pull the electron density from the benzene ring, making it more susceptible towards the attack from nucleophile. Now that's one reason. The other reason is that during resonance, the negative charge lands on ortho position and para position. So if there is an electron withdrawing group present there, it can take up the negative charge. It can disperse the negative charge over it. Especially when we talk about nitro group can disperse the negative charge over nitrogen and oxygen. Okay, so that leads to the stabilization. Okay, that is why nitro group at ortho and para position would increase the reactivity of haloarenes towards nucleophilic substitution. And if there is a nitro substitution at meta position, that does not make an impact simply because during resonance, the negative charge lands only on ortho and para position. it doesn't come on meta position. So even if there is a nitro group at meta position, it will not have any impact. The charge will not get, since it doesn't land on meta position, it will not get dispersed also. Okay. All right, next question. Identify the compound that on hydrogenation produces optically active compound from the following compounds. So these two are your compounds, A and B. Upon hydrogenation, they will give this. All that you have to do is remove the double bond. Okay, because hydrogen gets added across the double bond during hydrogenation, removing the in place of the double bond. So this is what you get upon hydrogenation. Now look, this carbon has bromine, hydrogen, methyl group and propyl group. 4 different groups. So this is a chiral carbon. Therefore, this is optically active. When we talk about this, bromine, hydrogen, ethyl group, and then again ethyl group. It does not have 4 different groups. Therefore, this carbon is not chiral. Therefore, this is not optically active, whereas this is optically active. Moving on. Which one of the following is a primary halide? Isopropyl iodide. Let's make the structure. This is isopropyl iodide. Secondary butyl iodide. Secondary butyl iodide would be CH3, CH, Cl, iodine, and then CH2, and then CH3. Okay, this is secondary because the carbon that it's attached to is attached to 2 other carbons. Okay, so this is your secondary butyl iodide. Tertiary butyl bromide, carbon attached to 3 different carbons. So the bromine atom is attached to a carbon which is attached to 3 other carbon atoms. This is your tertiary butyl bromide. Neohexyl chloride. Neo group is this. Okay, it has 5 carbon atoms. Now this is neohexyl, so these 5 and then CH2Cl. Okay, so this is neohexyl chloride, and as we can see that here the chlorine atom is attached to a primary group. Okay, only 1 carbon. So this is your primary halide. This is obviously tertiary halide, so not a primary halide. This is secondary halide, and this is also a secondary halide. Okay, so this is your answer. Okay, next question. Predict the products when this compound combines with alcoholic KOH. Now, alcoholic KOH, that means beta dehydrohalogenation. When we talk about beta dehydrohalogenation, that means we will be removing beta hydrogen. If this is the bromine atom, this is the alpha carbon, this is the beta carbon, the 2 hydrogens attached to it would be beta hydrogens. This would be beta carbon, therefore these 3 are beta hydrogens, and this would also be beta carbon, therefore the 2 hydrogens attached to it would also be beta hydrogen. So now these 2 positions are identical, same. Okay, so whether hydrogen is lost from here or here doesn't matter, the product would be same, but this is different. So let's see. So when the base abstracts this proton, these electrons shift here and bromide atom is released. Okay, so you will get this product. Okay, a double bond would come here, or you can do the same thing with this hydrogen also. The product would basically be the same. Okay, but when base abstracts, let's write it like this. When base abstracts this proton, these electrons shift here and the bromine atom is released. I'll actually, for clarity, I'll make this again. So this time the base is abstracting this proton, these electrons will go here and the bromide ion would be released. So the product that you will get is, okay, so one product is this, the other product is this. Next question, which of the following haloalkane would undergo SN1 reaction? So these are the haloalkanes available to you. Let's figure out which one is which. This one is a tertiary alkyl halide. Why? Because the chlorine atom is attached to a carbon which is attached to 3 other carbons. That makes it tertiary. This one is benzylic halide. This one is allylic halide. And this is primary halide. So bottom line is, when you have tertiary, benzylic or allylic halide, they undergo SN1 mechanism. Because they proceed via, because SN1 proceeds via the formation of carbocation, and benzylic carbocation, allylic carbocation and tertiary carbocation are very, very stable. Okay, this would undergo SN2 mechanism because it's primary halide. It's not very hindered. Okay, so nucleophile can come and attack and the chloride ion would leave in the next step. Okay children, so that's all for today. If you like the video, if it helped you in any way, please like, subscribe and share. And thank you for watching. Best of luck for your exams.